What is the absolute worst thing you can imagine happening to an aircraft in flight? An engine tearing away midair? A wing collapsing from structural failure? If those scenarios sound far-fetched, then keep watching, because what happened in 1959 might just change your understanding of early jet aviation forever. The story begins at the dawn of a new era. In the autumn of 1958, commercial aviation was undergoing a revolution. The Douglas DC-8 and the Boeing 707 had just entered service, marking the first time jet-powered airliners were introduced at scale in the Western world. While the British de Havilland Comet had already taken to the skies years earlier, its tragic history of catastrophic metal fatigue had led to numerous fatal accidents and grounded fleets, teaching engineers painful lessons about jet pressurization and structural integrity. The DC-8 and 707 were the West's answer: larger, faster, and, crucially, safer. But despite their promise, the industry had only scratched the surface of understanding what these new machines demanded from both pilots and engineers. Just a year after their debut, in the fall of 1959, Boeing was preparing to certify an upgraded variant of the 707, the 707-220. This model had been developed specifically for Braniff International Airways, a U.S. carrier that operated in demanding environments, including airports situated at high altitudes and in hot climates. These conditions significantly reduce air density, which in turn impacts engine performance and lift. To meet Braniff's operational needs, Boeing equipped the 707-220 with 4 Pratt & Whitney JT4A3 turbojet engines, each producing an additional 2,800 pounds of thrust over the earlier JT3C6 engines. These engines pushed the total thrust well past 56,000 pounds, granting the aircraft stronger takeoff performance and climb rates under adverse conditions. However, these gains came at the cost of fuel efficiency and noise, hallmarks of early turbojets that would soon be eclipsed by the advent of turbofans. With turbofan engines providing better thrust-specific fuel consumption and lower emissions, the 707-220 was destined to be short-lived. Only 5 were ever built, all delivered to Braniff. To prepare for the arrival of their first jets, Braniff sent a team of experienced pilots to Seattle to undergo transition training directly from Boeing. These weren't novice flyers. One of the captains had amassed 23,563 hours in the cockpit, over a career stretching back to 1936. The other had logged more than 450 hours. But none of that time had been in jets. Every minute had been spent flying propeller-driven aircraft. What they were about to encounter would be unlike anything they had known. In October 1959, after completing roughly 160 hours of ground school, covering the principles of jet propulsion, high-speed aerodynamics, and the specific systems of the 707, the Braniff pilots advanced to the next stage: hands-on flight training in the actual aircraft. There were no high-fidelity simulators to ease the transition. In 1959, flight simulation was in its infancy. Devices existed, but they were primitive, more like procedural trainers with static instruments and mock cockpits. They could not simulate realistic aircraft behavior, engine lag, or the nuanced feel of swept-wing jet handling. So, training was done in the air, in the real thing, and under real risks. On October 19, 1959, 8 people boarded a Boeing 707-220 at Boeing Field in Seattle for what was supposed to be a routine training flight. Among them were 4 Braniff crew members, 2 captains, a flight engineer, and a technical instructor, along with 3 Boeing personnel, a test pilot instructor, a co-pilot, and a flight engineer. Completing the crew was an FAA Air Carrier Operations Inspector, on board as an observer. The Boeing test pilot in command was only 33 years old and had logged about 5,000 hours total, including just 369 on the 707. While technically qualified, his experience on the aircraft was limited, especially given that the 707 had been flying commercially for over a year. The flight plan had been filed as an instrument round trip from Boeing Field, with a defined training area north of Seattle and an estimated fuel endurance of 5 hours, more than enough time to practice takeoffs, approaches, and engine-out procedures. At face value, this flight seemed well-staffed and carefully planned. But a closer look reveals a dangerous undercurrent running beneath the surface. Both Braniff captains were about to take control of a jet aircraft for the first time in their lives. These were men accustomed to the slower response and straightforward aerodynamics of propeller-driven aircraft. Jets, especially early turbojet models like the 707-220, demanded a completely different understanding of thrust lag, high-speed stall behavior, and energy management during approach. It's a transition that, as later investigations by the NTSB and ICAO would emphasize, cannot be underestimated. In fact, ICAO Annex 1 would later stress the need for standardized transition protocols, recognizing that pilots with thousands of hours in piston aircraft still faced a steep and dangerous learning curve when adapting to jet aircraft. The same lesson was reflected in reports on accidents like American Airlines Flight 1 in 1962, where improper pilot adaptation to jet systems played a critical role. Back in 1959, however, those lessons were still being written, sometimes in blood and wreckage. And on this particular day in Seattle, what began as a hopeful step into the jet age would soon become one of its earliest and most painful warnings. In 1959, there was no real substitute for in-flight experience. Flight simulators, as we know them today, simply didn't exist. There were procedural trainers, metal boxes with gauges, switches, and pedals, but nothing that could recreate the weightless sensation of altitude, the aerodynamic tension of high-speed turns, or the delayed response of jet thrust. So when pilots needed to learn how to fly jets like the Boeing 707, they had to do it the hard way, in the sky, with real engines, real speed, and very real consequences. And because of that, the era saw a spike in training accidents, many of which wouldn't have happened if simulators had been available to let pilots fail in safety before facing the real thing. Among the most critical lessons in jet training were phenomena unknown to piston-era pilots. Concepts like mock tuck, deep stall, and one particularly stubborn nemesis, Dutch roll. If you're not a pilot, the name might sound harmless, even quaint. But, as the Braniff crew would soon discover, Dutch roll is anything but trivial. To understand Dutch roll, you first need to picture an aircraft not as a rigid body, but as something dynamic, capable of rotating around 3 axes: pitch, roll, and yaw. Pitch lifts, or drops the nose. Roll tilts the wings. Yaw swings the nose left or right, like turning your head. Now, focus on yaw. In a swept-wing aircraft like the Boeing 707, yaw becomes more than just a simple motion. It becomes a trigger. Here's what happens. When the aircraft's nose yaws to the left, the right wing advances, cutting more directly into the airflow. Due to this geometry, the right wing generates more lift, not just because of its new angle to the air, but because it's also moving slightly faster through space. That increased lift causes the right wing to rise, initiating an uncommanded roll to the left. So a simple yaw, say from a gust of wind, becomes a combined yaw-roll motion. But it doesn't stop there. As the yaw angle increases, aerodynamic forces acting on the vertical stabilizer eventually push the nose back in the other direction, just like a weather vane. This counter-yaw then causes the left wing to advance and rise, rolling the aircraft in the opposite direction. The entire motion begins to oscillate, with yaw and roll chasing each other in a staggered rhythm. This is Dutch roll, an out-of-phase coupled oscillation that looks elegant on paper, but feels chaotic in the cockpit. Now, Dutch roll is a natural behavior in all aircraft to some degree, but it's much more pronounced in jets with swept wings, like the 707, the DC-8, or later, the Lockheed TriStar. The design that makes them fast and efficient near the speed of sound also makes them more vulnerable to these lateral oscillations. And though Dutch roll isn't inherently dangerous if it's well damped, it can quickly spiral out of control if left unchecked, especially when training pilots unfamiliar with the phenomenon. Engineers try to design aircraft with either stable or neutral Dutch roll characteristics. In a stable configuration, each oscillation gradually fades, like ripples on a pond after you toss a stone. In a neutral configuration, the oscillations continue at the same amplitude unless something intervenes, like an autopilot yaw damper or a pilot's input. But if the damping is insufficient, or the pilot reacts incorrectly, the motion can escalate into a dangerous instability. That's exactly what happened in multiple incidents, including the infamous United Airlines Flight 553 in 1972, where failure of the yaw damper system during approach contributed to a loss of control. Earlier, during the testing of the Convair 990 Coronado, Dutch roll tendencies were so severe that the aircraft required design modifications to be certified. But in 1959, these lessons hadn't yet been fully understood. Brunif's captains were going from the world of propellers, where yaw and roll were mostly independent, into an aircraft where they were tightly coupled, and sometimes unforgiving. And remember, this wasn't even a commercial flight. It was a training mission, designed to expose the crew to the very behaviors that could lead to disaster if not properly handled. That day, as the aircraft departed Boeing Field with a full load of crew and instructors, the skies were calm, but the stakes couldn't have been higher. This was not just a practice flight. It was a test of how much we understood about our own technology and how much we still had to learn. What the pilots didn't know was that Dutch roll wasn't just a theoretical quirk. It would soon become the very force they'd be fighting to survive. It wouldn't have seemed likely that things could get worse, but in aviation, worse always has a name. In this case, it was known as divergent Dutch roll, the very condition engineers hope to avoid at all costs. While normal Dutch roll is usually manageable, or at least annoying, divergent Dutch roll is far more sinister. In this scenario, each oscillation grows larger than the last, amplifying in a dangerous feedback loop until the aircraft either enters an uncontrollable spiral or the structural limits are exceeded. The stresses placed on the airframe by these combined yawing and rolling motions are not just theoretical. They can, and have, torn aircraft apart. The trigger for Dutch roll is often deceptively simple. A sudden gust of wind, a minor yawing motion, or even a slight atmospheric disturbance can set the cycle into motion. And if an aircraft has even a slight predisposition toward instability, something as mundane as a crosswind could evolve into a battle for control. That's why virtually every jetliner today, regardless of whether its Dutch roll tendencies are stable, neutral, or unstable, is equipped with a device called a yaw damper. This automatic system makes thousands of micro adjustments to the rudder throughout a flight, quietly neutralizing unwanted yaw and stopping Dutch roll before it ever begins. Modern yaw dampers are so seamlessly integrated that pilots almost never think about them. They're always on, always working, always in the background. Today, Dutch roll is still part of the academic training for airline pilots preparing for their ATP licenses, but it's rare to experience it in a simulator, let alone in a real aircraft. That's because it typically only manifests when the yaw damper fails, which in modern jets is a rare and heavily mitigated scenario. But in 1959, this was not the case. Dutch roll wasn't an afterthought. It was front and center, part of the core training syllabus, introduced as early as the first flight. And there was a good reason for that. Back when Boeing first developed the 707, aerodynamic understanding of swept-wing flight was still evolving. The earliest models of the 707, including the 707-120 and the 707-220, exhibited mildly divergent Dutch roll characteristics. The divergence wasn't dramatic. The oscillations grew only slightly with each cycle, but they wouldn't damp out on their own. Intervention was necessary, either from the pilot or an automated system. The 707 was fitted with a yaw damper to handle this, But in its early form, the system was rudimentary by today's standards and introduced problems of its own. Unlike modern yaw dampers, which operate electronically and isolate their control forces from the pilot's feet, the early 707's yaw damper was mechanical, feeding its rudder inputs directly back through the control cables to the rudder pedals in the cockpit. This meant that pilots could actually feel the damper working beneath their feet, a constant, unprompted pressure that could become a serious issue in emergency situations, particularly during engine failures. Engine failures in multi-engine jets cause asymmetrical thrust, which tends to yaw the aircraft toward the dead engine. To correct this, the pilot must apply rudder into the live engine side. But if the yaw damper was still engaged, it would resist this movement, countering the pilot's corrective inputs. And at low speeds, such as during takeoff or landing, rudder authority is reduced. In those moments, pilots already need to apply significant force to keep the aircraft on course. With the yaw damper fighting back, that force could become dangerously high, requiring such aggressive pedal input that the pilot might not be able to maintain control at all, especially at low altitudes, where there's no room to recover. To prevent this, the standard procedure on early 707s was to disconnect the yaw damper during critical phases of flight. It would be disengaged before takeoff and remain off until the flaps were fully retracted. Similarly, during landing, it would be disabled when full flaps were selected. But there was a trade-off. With the yaw damper off, the aircraft was again vulnerable to Dutch roll, and not just ordinary Dutch roll, but an aggravated form. That's because Dutch roll tendencies worsen when the flaps are extended. So, ironically, the moments when the yaw damper had to be turned off were the very moments when the aircraft was most susceptible to instability. This made Dutch roll not just an academic topic, but a survival skill. Pilots had to understand the dynamics, recognize the symptoms, and execute the recovery perfectly, often within seconds. Fortunately, the recovery technique was relatively simple in theory. Apply roll inputs opposite to the direction of the bank. If the aircraft was rolling right, apply left aileron. This would gradually reduce the roll amplitude and bring the wings level. As for the yaw motion, it could either be stopped with rudder input or allowed to subside naturally. On the 707, keeping the wings level was often sufficient to damp the yaw. But there was a subtle psychological challenge buried in this technique, something that would haunt many early jet pilots. Because Dutch roll is a phase-lagged motion, the aircraft can be banked left while already beginning to roll right. In that moment, the correct input is counterintuitive. The pilot must apply more left aileron, even though the left wing is already low. The goal is to stop the rolling motion, not the bank angle. But that feels wrong. Instinct pushes the pilot to level the wings, pushing the stick right, which only fuels the rolling energy and makes the situation worse. This mental hesitation, the moment of internal conflict between instinct and procedure, could spell disaster if it occurred during a critical phase of flight. And unfortunately, for the Braniff crew on board the training flight that day, Dutch roll wasn't a theoretical footnote. It was about to become very real. And this time, there would be no simulator, no instructor pause button, and no room for error. It's one thing to understand Dutch roll in theory, how to counter it with roll inputs against the motion, how to dampen the oscillation without overcorrecting. But applying that theory inside a metal tube at 10,000 feet is something else entirely, especially when you've never flown a jet before, especially when you're sitting next to someone who's supposed to be your safety net, but instead is about to push the aircraft beyond its intended limits. At 13:30 local time, the Boeing 707-220 lifted off from Boeing Field in Seattle. With 8 people on board, 4 from Braniff, 3 from Boeing, and 1 FAA inspector, the aircraft climbed northward toward its designated training area. The sky above the Puget Sound was thick with overcast, the cloud base sitting around 4,000 feet. The pilots likely leveled off somewhere between that and 10,000 feet, low enough to replicate approach behavior, high enough to offer a margin for error. Or so it seemed. The cockpit was unusually crowded. All 8 occupants had come forward to observe the exercises, an uncommon practice today, but not unheard of in the looser training environments of 1959. In the left seat sat the Boeing instructor, guiding one of the Braniff captains, an experienced pilot in props, but a complete novice in jets, through a series of basic maneuvers. First, the instructor demonstrated. Then, the trainee mirrored. This instructional method, known as patterning, is standard fare in aviation training, helping to build motor memory and procedural flow. The initial maneuvers were simple: turns, climbs, descents. But soon, the complexity escalated. The instructor disengaged the yaw damper and initiated a Dutch roll demonstration in clean configuration, with flaps and slats fully retracted. At high speed and in clean trim, Dutch roll is relatively benign. The oscillations are slow and shallow. With the instructor coaching him, the Braniff captain executed the recovery with little difficulty. But that was just the warm-up. Next came the real test. Dutch roll with full flaps extended to 40 degrees. This configuration mimicked final approach, the phase of flight when aircraft are at their slowest, their drag highest, and their control margins thinnest. In this setup, the 707 was at its most vulnerable to yaw-induced instability. The instructor slowed the aircraft to 155 knots and began deploying flaps. There is no exact record of the altitude at this point, no cockpit voice recorder, and the flight data recorder wasn't yet wired in. In 1959, FAA regulations only mandated recording devices for passenger flights, not training missions. But based on the cloud base and airspeed, investigators later estimated the aircraft was likely around 10,000 feet. Once stabilized at low speed, the Boeing instructor initiated another Dutch roll sequence, this time with the yaw damper off and the flaps fully deployed. The bank oscillations began, but something was immediately wrong. The instructor's control inputs were aggressive, far more aggressive than what was recommended. According to Boeing's own training manual, Dutch roll demonstrations should use bank angles no greater than 15 degrees, with an absolute maximum of 25 degrees. But this instructor was exceeding that by a lot. One of the Braniff instructors, alarmed by what he was seeing, leaned over and reminded the Boeing pilot of the limitations. The instructor acknowledged the warning, but then ignored it. Instead of dialing it back, he pressed further. There's a term for this kind of flying: overconfidence masking as competence. Whether it was ego, complacency, or a desire to impress, the Boeing instructor continued to input excessive bank angles in a configuration where even small deviations could snowball into instability. And remember, this was not a demonstration flight for seasoned jet crews. This was day one of training for a captain who had never flown a swept-wing jet in his life. The instructor was pushing the aircraft into the very edge of controllable flight, then handing over the controls to a trainee who didn't yet have the instinctive feel for jet dynamics. Looking back, it's astonishing that Dutch roll recovery was introduced this early in a transition program. In modern jet training, pilots might spend dozens of hours in simulators before they even touch a yoke in real life. To teach something as nuanced and potentially dangerous as Dutch roll on the very first sortie now seems reckless. But in 1959, the lines between training and testing were often blurred. The Boeing instructor, apparently undeterred by his colleagues' concern, suggested switching seats with the Braniff captain so that the trainee could experience recovery from the left seat, the captain's seat. The trainee agreed, and they swapped positions. Then, astonishingly, the instructor initiated yet another Dutch roll, despite the previous warnings. Only this time, he pushed even harder. With the yaw damper still disengaged and flaps at 40 degrees, the instructor rolled the aircraft from side to side, with control inputs well beyond the prescribed safety margins. Instead of keeping bank angles within the 25-degree threshold, he allowed the wings to roll as much as 60 degrees in both directions, turning a carefully designed training scenario into a high-risk roller coaster. In swept-wing jets, like the 707, these kinds of maneuvers can quickly become unrecoverable. The combination of low airspeed, high drag, and exaggerated bank angles creates a perfect storm where oscillations can build faster than a pilot can correct them. The aircraft had now entered the realm where training ends and survival begins. And the Braniff captain, just an hour into his very first flight in a jet, was suddenly the one in command. The Braniff captain, sitting in the left seat of the Boeing 707 for the very first time in his life, hesitated as the aircraft began to sway. The Dutch roll had started gently, but each cycle grew more urgent, more pronounced. He allowed several oscillations to pass, the aircraft slipping left, then right, as he tried to process what was happening. Then, in a surge of nervous resolve, he gripped the yoke and committed to a recovery. But he made a fatal mistake. He turned the yoke in the wrong direction. This is the critical point where textbook knowledge collides with instinct. As the aircraft's left wing, still lower than the right, was rising in the natural cycle of the Dutch roll, the correct input was to apply left aileron to oppose the roll. But the captain, reacting to what he saw instead of what he understood, applied right aileron, accelerating the roll rate dramatically. In seconds, the aircraft rolled sharply to the right, the bank angle increasing past 90 degrees, placing the massive jet into a near-inverted position. The instructor lunged to take control. But by then, the situation had already begun to spiral. Trained in the recovery techniques of the early jet era, which favored sharp, assertive aileron inputs, he reacted forcefully, too forcefully. Instead of counteracting the motion and damping it, his input overcompensated. The 707 snapped into a left roll even faster than the previous right. The aircraft was now caught in a deadly rhythm of alternating violent bank angles. Severe pilot-induced oscillations, PIOs. In modern training, PIOs are well understood. They occur when a pilot's control inputs are out of sync with the aircraft's response time. The human brain, wired to expect immediate feedback, often applies more input when it doesn't see an instant result. But jet aircraft, especially large ones, don't respond instantly. So when delayed feedback finally comes, the pilot has often already applied additional control input, pushing the plane beyond its intended motion. The result is a loop of overcorrection, an escalating tug-of-war between aircraft momentum and human instinct. And if left unchecked, these oscillations can become divergent, growing with each swing, until the structure fails. This wasn't theory. It had happened before, most infamously in American Airlines Flight 587 in 2001, where excessive and rapid rudder reversals in response to wake turbulence caused the vertical stabilizer to shear off, leading to a catastrophic crash in Queens, New York. There, the pilot's aggressive inputs caused forces on the tail structure that exceeded design limits. In the case of this 707, however, the stress was being absorbed not by the tail, but by the wings and the engines hanging from them. Jet engines are among the densest and most massive components on an airliner. When subjected to rapid directional reversals, they become pendulums of momentum. Their inertia resists change. The faster the aircraft rolls left, then right, then back again, the more violent the forces acting on the engine pylons become. And at some point, the forces required to reverse their motion surpass the tolerances of the structure holding them in place. Aircraft designers understand this. That's why engine pylons are built with fail-safe mechanisms, not to protect the engines, but to sacrifice them in order to save the wing. The pylons are designed to break away under overload, to avoid catastrophic wing failure. And that's exactly what happened next. Amid the chaos of the rolling aircraft, 3 explosive bangs echoed through the fuselage. The throttle levers for engines 1, 2, and 4 snapped back to idle and then went slack. The control cables, which ran from the cockpit throttles to the engines under the wings, had been severed. The engines were gone, or nearly so. But that wasn't immediately clear from the cockpit. All the crew knew was that they had just lost control of 3 engines, and the aircraft was still not stable. The Boeing instructor, fighting the yoke, managed to arrest the oscillations, but by then, the aircraft had completed almost a full inversion. The nose was pointed toward the ground in a shallow dive. With little altitude to spare, the instructor committed to a full barrel roll, using the aircraft's remaining roll momentum to carry them through and return the wings to level. He succeeded. The aircraft exited the maneuver in a medium dive, airspeed climbing rapidly. The 707 was fast approaching structural limits, but the instructor managed to stop the descent without further overloading the jet. There was no cheering in the cockpit, just stunned silence, and a dawning realization that they were now flying on one engine. The FAA inspector volunteered to go back into the cabin and assess the situation visually. As he peered through the passenger windows, the full scale of the damage became horrifyingly clear. Engines 1 and 4 had completely separated from the wings, their pylons sheared off by the violent oscillations. Engine 2 was still attached, but only barely. Its pylon had partially failed, and the engine now hung at an angle, tilting upward, with its exhaust blasting directly into the fully extended trailing edge flaps. The aircraft was damaged, wounded, and unstable, and it was still flying. Fire was now licking at the open wounds where engines had once hung, pouring from the raw, torn metal of the left wing. As the number 2 engine finally separated from its pylon, it left behind more than just a gap. It tore open fuel lines still pressurized with jet fuel. Flames erupted, fed by the volatile stream, turning what had been a catastrophic control failure into a full-fledged in-flight fire. When the FAA inspector returned to the cockpit and reported the blaze, the Braniff technical instructor turned to look out the window and confirmed what had happened. Engine 2 was gone, and in its place was a growing inferno consuming the inner wing structure. Down on the ground, near Lake Kavanaugh, north of Seattle, residents stood in uneasy silence. They had heard the roar of the jet, muffled and distant above the thick, overcast sky. Moments later came a sound unlike anything they had heard before, a dull, resonating thump. Then 3 massive Pratt & Whitney JT4A turbojets dropped from the clouds like meteors, tumbling through the air in eerie silence. There was no airplane in sight. Only those 3 engines, now orphaned, falling alone through the sky. No one on the ground could fully grasp the scale of what was happening in the sky above them, but those engines falling like debris told a story too big to ignore. Back in the cockpit, the pilots were flying a wounded jet in survival mode. The Boeing 707 had never been designed to fly on one engine, but now it had no choice. In normal circumstances, this flight configuration would have been impossible, but this was not a normal aircraft anymore. It was empty. No passengers, no cargo, and with 3 engines lost, the overall weight was significantly reduced. Ironically, the loss of mass gave the aircraft just enough lift to limp along, but it wasn't enough to save it. Not with a raging fire eating through the wing, and not with most electrical systems dead due to the loss of all but one generator. Without electrical power, the cockpit had gone eerily silent. Vital systems were offline. Instruments flickered. Even the hydraulic pumps powering the rudder had failed, forcing the pilots to rely on brute leg strength to muscle the control surfaces through mechanical linkages. The Boeing instructor took the controls and eased the aircraft into a shallow descent, hoping to trade altitude for airspeed while minimizing structural strain. As the aircraft dropped below 4,000 feet, the Braniff crew spotted Lake Kavanaugh through the thinning cloud cover. The technical instructor suggested a water ditching, reasoning it might be their only chance. But the instructor disagreed. He believed he could find a better spot, and turned away from the lake, guiding the burning jet toward a narrow valley near the Stillaguamish River. As the aircraft burst through the clouds, those on the ground finally saw it, what was left of it. A Boeing 707, trailing fire like a comet, with 3 engines missing, its left wing ablaze, flames pouring down the fuselage and licking at the tail. Inside, chaos met cold resolve. The second Braniff captain strapped into a jump seat in the cockpit, while the Braniff flight engineer, the technical instructor, the Boeing co-pilot, and the FAA inspector all moved to the tail section, thinking it would offer the best odds in a crash landing. That split-second decision, where to sit in a dying aircraft, would become the pivot point between life and death. From their seats in the tail, the 4 men had a direct view of the fire as it consumed the left wing. The heat was so intense, it had begun to bubble the paint on the vertical stabilizer and crack the cabin windows. Through the flames, the inner structure of the wing was now visible. Stringers, spars, fuel lines, all glowing red or disintegrating into smoke. The inferno had burned a hole through the inboard flap, and worse yet, had completely destroyed the inboard aileron on the left wing. In the Boeing 707's design, roll control relied on both inboard and outboard ailerons. But they weren't independent. With flaps extended, the outboard ailerons received their movement from the inboard ones, and with the left inboard aileron now burned away, the left outboard aileron was effectively useless. According to the accident report, only the right inboard aileron and the right outboard spoiler remained functional, giving the crew just 3/8 of the normal roll control authority. That alone would have been a monumental challenge, but the situation was even worse. The rudder, a critical backup for roll control in asymmetric thrust conditions, was barely usable. With the hydraulic system disabled, it could still be moved manually, but only with tremendous force, the kind that requires full body weight and physical strength. And it would have to be used, because Engine 3, the only one left, was creating a powerful asymmetric thrust, yawing the aircraft right. Meanwhile, the fire on the left wing was generating huge aerodynamic drag, further unbalancing the aircraft. The fuel-fed blaze had by now burned a 35-square-foot hole in the upper surface of the wing, radically altering its aerodynamic profile and further sabotaging lift on the left side. The airplane was fighting itself. Asymmetrical thrust, lopsided drag, destroyed ailerons, compromised flaps, and an expanding fire that showed no signs of slowing down. They were flying on instinct now, on judgment, on sheer will. The crippled Boeing 707 was in its final fight for survival. With the left wing torn open and burned hollow, it now generated far less lift than the right. The aircraft wanted to yaw violently to the left while simultaneously dropping that wounded wing. The pilots tried one last adjustment. They retracted the flaps from 40 degrees back to 28. It helped, slightly. Roll control improved just enough to offer a whisper of hope, but it was still a losing battle. The combined effect of asymmetric thrust from the lone surviving engine and the drag from the wing fire was nearly impossible to overcome. As the aircraft descended into the river valley, the crew scanned desperately for a landing site. Miraculously, they spotted an open field, maybe just long enough, but the 707 was on the brink. Then, another jolt. An explosion shook the airframe as superheated fuel vapors from the damaged tanks ignited, sending molten aluminum trailing behind them like falling embers. Parts of the left wing skin peeled away, folding backward in midair, spiraling down into the trees below. The pilots attempted to slow down, but as they did, the already limited control authority deteriorated. Slower airspeed meant less airflow over the damaged control surfaces, which meant even less ability to counteract the yaw and roll. If they couldn't reduce the asymmetry or regain control, they would risk a flat spin or uncontrollable bank before they even reached the ground. There was no more room to climb, no more thrust to give. So the Boeing instructor made a choice as desperate as it was logical. He shut down the last working engine to reduce the yawing imbalance. It was a move of raw airmanship, but it also sealed their fate. With the final engine silenced, the descent rate increased sharply. They were too low, too heavy, and too unstable. It became clear they wouldn't make the field. The trees came fast. At 33 meters above ground, the aircraft's belly clipped the forest canopy, scattering branches and shearing leaves like paper. Then came 120 meters of open land, a fleeting stretch of green that offered no refuge. The aircraft struck a stand of trees. One thick trunk tore off the outermost 5 meters of the already damaged left wing, forcing the jet into a rapid left roll. The plane pitched and rolled violently as it burst from the forest's edge, skimming across the shallow waters of the Stillaguamish River. By now, the aircraft was banking left more than 45 degrees, the wingtip nearly grazing the water. Then came the final impact. The fuselage slammed into the opposite riverbank. A massive fireball erupted, engulfing the aircraft in flame as it cartwheeled and crumpled, tearing itself apart. The forward fuselage was obliterated, consumed by the impact and explosion. But the tail section, miraculously, stayed intact. It slid across the muddy gravel, skimming back into the river's shallows, where it finally came to rest, broken, smoldering, but still whole. Inside that tail section, 4 men had survived: the Braniff flight engineer, the technical instructor, the second Boeing pilot, and the FAA inspector. Those who had moved to the rear in those final moments escaped with their lives. Only one of them was seriously injured. But those who stayed in the cockpit, the Boeing instructor, the Braniff captain in the left seat, and the other front crew members, were killed instantly in the first, devastating impact. The Civil Aeronautics Board, the forerunner to today's NTSB, concluded that the probable cause of the accident was the structural overload of the engine pylons resulting from excessive and improper control inputs during the Dutch roll demonstration. The Boeing instructor, attempting to showcase the maneuver, had pushed the aircraft beyond its aerodynamic and structural limits. But the story didn't end there. Investigators from Boeing and the FAA agreed that while pilot error had triggered the chain of events, design shortcomings had amplified the consequences. The original yaw damper system, which transmitted force directly back to the rudder pedals, created conflicting control inputs during engine-out scenarios. The lack of backup hydraulic power for the rudder made roll recovery nearly impossible under electrical failure. And most critically, the 707's vertical stabilizer was found to be too small to provide adequate directional stability in deep Dutch roll. As a result, Boeing implemented a series of sweeping improvements. The vertical stabilizer was enlarged, and a ventral fin was added to the underside of the fuselage to improve yaw stability. These changes meant that during a Dutch roll, the aircraft would now correct itself sooner and more smoothly, before instability could take hold. The yaw damper system was also redesigned so that its inputs no longer fed back into the pedals, allowing it to remain engaged throughout the entire flight. And most importantly, redundant hydraulic systems were installed for critical surfaces, ensuring that even in an electrical failure, pilots wouldn't have to rely on sheer physical strength to control the aircraft. Today, a crash like this is virtually unthinkable. Not because jets have become invincible, but because training philosophy and technological safeguards have evolved. With the advent of full-motion flight simulators, pilots can now train in extreme scenarios without ever leaving the ground. They can experience Dutch roll, engine failures, and control losses without endangering lives or aircraft. But the core lesson remains. In any non-fly-by-wire aircraft, there is no system to limit how much the pilot can move the controls. That means, even today, a series of excessive, rapid, opposite control inputs can overstress the airframe and tear it apart. This isn't just theory. It's real. It's happened. And pilot-induced oscillations like the ones that doomed this training flight still surface in accident reports from time to time. So if you're a pilot, this story isn't just history. It's a warning. A reminder that confidence must always be tempered by caution, and that knowing what a machine can do is never an excuse for testing how far it can bend. And for the rest of us, Imagine sitting on a plane while the pilots up front are experimenting. Playing. Pushing. You'd never want that. But sometimes that's exactly what happens.